ATP synthase is a molecular machine that works like a turbine to convert the energy stored in a proton gradient into chemical energy stored in the bond energy of ATP. The flow of protons down their electrochemical gradient drives a rotor that lies in the membrane. It is thought that protons flow through an entry open to one side of the membrane and bind to rotor subunits. Only protonated subunits can then rotate into the membrane, away from the static channel assembly. Once the protonated subunits have completed an almost full circle and have returned to the static subunits, an exit channel allows them to leave to the other side of the membrane. In this way, the energy stored in the proton gradient is converted into mechanical rotational energy. The rotational energy is transmitted via a shaft attached to the rotor that penetrates deep into the center of the characteristic lollipop head, the F1 atpase, which catalyzes the formation of ATP. The F1 atpase portion of ATP synthase has been crystallized. Its molecular structure shows that the position of the central shaft influences the conformation and arrangement of the surrounding subunits. It is these changes that drive the synthesis of ATP from ADP. In this animated model, different conformational states are lined up as a temporal sequence as they would occur during rotation of the central shaft. Like any enzyme, ATP synthase can work in either direction. If the concentration of ATP is high and the proton gradient low, ATP synthase will run in reverse, hydrolyzing ATP as it pumps protons across the membrane. To show the rotation of the central shaft, a short fluorescent actin filament was experimentally attached to it. Single filaments attached to single F1 ATPases can be visualized in the microscope. When ATP is added, the filament starts spinning, directly demonstrating the mechanical properties of this remarkable molecular machine.